Now that we have cleared the definitions of the two concepts, namely conditional probability and independence, let's look into Bayes' theorem, which is based off conditional probability. So Bayes' theorem basically states this mathematical statement. The conditional probability of A given B is actually the product of conditional probability of B given A multiply probability of A divided by probability of B. So why does it make sense? Well, we can look at the definition of conditional probability. That is, conditional probability of A given B is actually probability of A intersect B divided by probability of B. Look at it the other way around. The conditional probability of B given A is actually also the probability of A intersect B. However, this time you divide it by probability of A. Since both expression uses probability of A intersect B, let's get another way to write probability of A intersect B. Well, probability of A intersect B is actually probability of B given A multiply probability of A. So this comes from the second line. Then if you sub this expression into the first line, then you realize that you get back to the Bayes' theorem, which is the probability of A given B is actually probability of B given A multiply probability of A divided by probability of B. A more complicated version of Bayes' theorem actually looks like this. So why does this make sense? Well, we know that the left-hand side and the part that is above the hyphen actually resemble to the original, the simplest form of Bayes' theorem. The only difference is that the denominator looks slightly different. Okay, so let's see how does the denominator equal to each other. Well, so PB, which is the denominator in the first expression, can be re-expressed using a Venn diagram. So let's draw one. Let's draw a box first, then two circles. And then you realize that probability of B can actually be re-expressed as the sum of the red area and the black area, correct? So how do you express the red area? The red area is actually exactly P A intersect B, correct? And the black area is A complement intersect B. And we know that probability of A intersect B is actually probability of B given A multiply probability of A by definition of conditional probability. And then if you look at the second part, by definition of conditional probability, we know that this expression is the same as probability of B given A complement multiply probability of A complement. And then you realize that this expression is exactly the denominator in this longer form of Bayes' theorem. So that's why this whole expression highlighted in green makes sense and is equivalent to the simpler form of the Bayes' theorem. So now let's use Bayes' theorem to solve some real problems. Well, let's look at this problem quoted from Bruce Hansen's probability textbook. So suppose there is 1% of the athletes uses banned steroids, and suppose a drug test has a detection rate of 40% and a false positive rate of 1%. If an athlete tests positive, what is the conditional probability that the athlete has taken banned steroids? We already know that we are going to use Bayes' theorem, so it's very important for us to identify the events A and B. So here, let's define event A to be that the athlete actually take banned steroids. So what is A complement? That is, the athletes do not take banned steroids. And event B is actually being detected for the use of banned steroids. And we are actually asked, given that the athlete has already been tested positive, what is the conditional probability of the athlete actually taking the banned steroids? Alright? So the question is actually asking for the conditional probability of A given B. By Bayes' theorem, we know that the conditional probability of A given B is actually the probability of B given A multiply probability of A divided by probability of B given A multiply probability of A plus probability of B given A complement multiply probability of A complement. So let's look at each of the terms in this complicated expression. Term by term, we will be able to find out them, and then we can compute the probability of A given B. Alright, so the first term is actually probability of B given A. Well, what does that mean? It means that given the athlete actually takes in banned steroids, what's the chances of these athletes being tested positive? That is 40%, right? That is the exact definition of detection rate here in the question. Okay? So, another expression that we are interested in is probability of A given A complement. That is, given that the athlete actually do not take in banned steroids, what's the chances of the athletes being tested positive? That is 1%, because this is the exact definition of false positive, correct? And now, what is probability of A? That is simply the percentage of athletes that uses banned steroids, correct? So that is also 1%. PA complement would be 99%. With these four numbers, we will be able to compute the conditional probability of A given B. So here, let's just sub in the values. That is 40% multiply 1% divided by 40% multiply 1% plus 1% multiply 99%. So eventually, your answer would be 28.77%.